All right, as promised, I will try to make up for the time we missed in the snow. Maybe just to get to the point here. We were talking about linear transformations of column vectors, right? And there's a theorem which you should know about. Theorem 4.2.21, which is on page 141. And it's a very, very nice theorem because I've asked you a number of questions in the homework, like, so here's a transformation from some set of column vectors to another, and I said, you know, is this linear transformation, is it injective? Is it surjective? Is it a bijection? Does an inverse exist? And all of those questions, in part, can be answered by this theorem. It's really simple. If we have a linear transformation L from Fn to Fm, okay, column vectors, all right? And the standard matrix, as we proved, exists today, L, which would be an element of the m by n matrix over the field. Then L is 1 to 1, or L is injective, if and only if, all right, the columns of the standard matrix are linearly independent. The columns form a linearly independent set. Columns of the standard matrix form a linearly independent set. All right, obviously subset of Fm. And 2, L is onto, or you could say L is a surjection, onto Fm, if and only if the columns of L, of the standard matrix L, span Fm. Of course, this I have a formula for. In other words, I could say if the column space of the standard matrix is equal to Fm, in other words, then it's onto. All right. The proof of these propositions is given on page 141. I will go through them briefly here. So first of all, L is 1 to 1, if and only if what? If and only if L of x equals to 0, if and only if x is equal to 0. We proved that the other day, remember? So that's the statement that it's 1 to 1, it's injective, right? If the kernel is just the 0 vector, that's what that says. But goodness gracious, that's exactly the same as the statement that standard matrix of L, right, times x is equal to 0, if and only if x is equal to 0, all right? And what does the last equation say? The last equation, what is this? Well, that's exactly column 1, right? Column 1 of L times x1 plus da-da-da plus xn, column n of the standard matrix of L equals to 0. If and only if what? If and only if c1 equals to x1 rather. The x1, x2, xn, they're playing the role c1 through cn, usually does in our arguments. In other words, that says that the columns of the matrix form a linearly independent set. And these are reversible statements, so that's if and only if. One of you asked me if we can give a proof that goes both directions at once. Here's an example of one of those. Then to prove 2, all right, L is onto F. So let's see here. L is onto Fm. What's that mean? That's just saying if and only if for each, let's say, W in Fm, there exists, let's say, X in Fn such that what? Such that L of X is equal to W, right? But that's interchangeable with the statement that for each W in Fm, there exists X in Fn such that what? Such that the matrix of L, right, times X is equal to W. But what that's saying is that, of course, we proved before, this means that W is an element of the column space of the matrix, right? And that's it. The columns of L span as interchangeable with L being onto. All right, so there you go. You can check whether a linear transformation is one-to-one and onto simply by looking at its standard matrix and studying its properties, which is very nice. Now, section 4.2, which I'm not going to write, but I would encourage you to read. There's a nice selection of examples. Example 4.21 on page 132 through example, let's see here. Man, there's a bunch of them here. Through example, so many examples, goodness gracious. So, you can read through these pretty fast. You're just looking to get a sense of what linear transformations do. All the way through page 140. We proved the fundamental theorem of linear algebra today on 140 already. But if you look at those examples from page 132 to 140, you'll get a sense of what linear transformations do for linear transformations going, say, from Rm to Rn. And there's also a nice little theorem in there which shows you that a linear transformation maps a line to another line, or possibly a point. We could generalize that theorem to show that a linear transformation maps a linear manifold to another linear manifold, although I don't think that's currently in my notes. But it would be a good thing to add. All right, that brings us to section 4.3. All right? So, let me erase this. Now, I guess I could give you, before I get to 4.3, let me give you an example of how to apply this theorem real briefly. Let's see here. So, for example, if I have, let's say, L of x, y, z equals to, x, comma, x plus y plus z, all right? I'll just stop there. You can figure out, is this one-to-one? Is this onto? Is it possible to invert it, all right? Is it possible to find an inverse? And so the standard matrix of L, all right? And sometimes, I go back and forth, what's the best way to find the standard matrix? Sometimes it's just most convenient to just kind of like stare at the formula and figure out what it has to be. Here, L is a mapping from R3 to R2. Okay, R3 to R2 by the formula, which shows me I'm looking for a 2 by 3 matrix. 2 rows, 3 columns. So, all right, so let's see here. So I've got 1, let's see here, 1, 1, 1, 0, 1, 0, 1. And just to be safe, I'll think about checking it. Multiply this, right? Multiply this times that. You get back to x for the first spot, x plus y plus z for the second spot. There you go. That's the standard matrix of L. All right. Now I made it simple on purpose. You can see that the reduced row echelon form, and I probably don't even really need to calculate that, but if you do, it's pretty clear what you get. You get 1, 0, 0, 0, 1, 1. Okay, so I can see that the column space of the standard matrix is what? It's the span of the first 2 columns, 1, 1, and 0, 1. Anyway, it's exactly the whole kit and caboodle. It's R2. So, done, surjective. So this mapping is surjective because the column space is equal to the codomain. Is it injective? Well, doesn't look good because remember, we have a rank nullity theorem. I guess we haven't quite got to that yet, but I don't know if I have that to work with here. I know I have a rank nullity theorem for matrix, but let me just calculate directly for the moment. If you look at the equation L of x, y, z equals to 0, what's in there? I mean, you can see it from this, right? This says that we have x equals to 0 and we have y plus z equals to 0. Well, that permits lots of solutions. So in other words, a typical element in the kernel is something like, let's see here, 0, and I guess I can say y is equal to minus z, right? So it's something like minus z, z. That's an element of the kernel. I don't know, what do you want to look at? It's the null space. You can either look at it, it's in the null space of the standard matrix, right? But you can easily see that that's the same as the kernel of L in this context. Those are equal. So, and that's true for any Z, right? So in fact, the kernel of L is the span of 0, minus 1, 1. As you can see, that's not equal to the 0 vector, right? Not the whole set, at least. I mean, 0 vector's in there, but it's not equal to the set just containing the 0 vector. Consequently, L is not injective. All right, so this function is surjective, but not injective. The only way the function can be invertible is if it's both injective and surjective. So unless you got both, we can't find an inverse. Not in this sense, at least. All right, so that's that. So let's move on to. So I've asked you a few questions like that in the homework. These are not meant to be tricky, and I often ask questions like this on a test because I feel like if a student really understands how to answer this question confidently, well, they have a good part of the heart of this course. Okay? So don't assume that all the questions on the test are impossible. There can be fairly simple questions. It's, you know, but they won't be simple unless you understand the theorems here, right? You have to know what the words mean, otherwise questions seem hard, even when they're not. All right. You're like, well, any question I understand is an easy question. I know it. All right. Section 4.3, restriction, extension, isomorphism. So definition, these are really, really nice, beautiful results. If we have T a linear transformation from V to W, okay, again, a linear transformation over vector spaces.
2 o'clock p.m.
Silence. Vector spaces over a field F. And if we have U is actually this, I mean, I guess I'm giving the definition. You can define a restriction for just a function. You don't need linearity per se. For a subset of V, then we define, I guess this is just set theory at the moment, T restricted to U is a new function. The domain of the new function is U. Its codomain is still W. And it's very boring. It's just like T restricted to U of X is just equal to T of X for all X in U. So basically the restriction is just like keep the same formula but change the domain. And you know, just as a point of language, we say T bar U like this is quote unquote T restricted to U. All right. Proposition. If you have a linear transformation, all right, and you restrict it to a subspace, then the restriction is also a linear transformation. So here we go. Theorem. If T is an element of the linear transformations from V to W, and U is a subspace of V, then T restricted to U is itself a linear transformation from U to W. Okay. Proof. I mean, I don't know if I'll write it down, but it seems rather silly to even bother writing it. T restricted to U if I let it act on Cx plus Y, where Cx plus Y is an element of well, what is it? Gotta be careful here. I worked myself into a corner. Let X and Y be elements of U and C be something in the field. Consider T restricted to U of Cx plus Y is equal to what? Well, first of all, notice that, I'll write up here, note Cx plus Y is an element of U again, as U is a subspace of V, right? So a subspace is closed under linear combinations. So I have that this is an element of U, therefore by the definition of restriction, this is simply T of Cx plus Y. But hey, T is a linear transformation, I'm assuming that. So this is Ct of X plus T of Y. Sorry, I forgot to say that. Let T be linear. There. I should just say at the start, let t and u be as in the statement of the theorem, and then I would be good to go. Oh well, I forgot to do that. All right, so anyway, t is linear transformation, x and y and u. Here we go. So I have c times t of x plus t of y, but by the way, that's c times t restricted to u of x plus t restricted to u y, because x and y are again in u, and that's the definition of the restriction, but there you have it. Since x and y are arbitrary and c was an arbitrary field element, it follows that t restricted to u is homogeneous and additive, and consequently linear transformation. All right. Not especially surprising. Oh, there's a typo in my notes. I got a little u where I meant to have a big U. Sorry about that. Weird. On page 143 at the bottom. All right. Now, the other side of things, right, is you can talk about a restriction, right? So the place in Calculus 1, or maybe pre-calculus, we talk about that is, you got something like the sine function, right? That's a typical thing. It goes on and on and on and on, right? And then you talk about inverse sine. Well, inverse sine is actually, it's just the inverse for just the restriction of sine to this little branch from minus pi over 2 to pi over 2, right? So that's the idea of a restriction maybe you've seen before. An extension, what's an extension? Well, that would be something like this. Here, somebody gives you, like, you kind of always has these problems. Like you've had a homework problem like this, right? And then they ask you some kind of vague question about the graph of the function. You're like, I don't know what happens past the picture I'm given. See, there you're facing the problem of extension. And the thing with extension is there's lots of different ways you could go. Like, I don't know, maybe it does this past what you're given in red, you know? Or, just to illustrate another possibility, the extension of the given red function here could be, I don't know, it could do this. And maybe it does this. I mean, who knows? Past the window that you're given, how could you extend a function? Man, infinitely many ways, right? The problem of extending a function is totally open. There's so many ways. Now, restriction, in contrast, is unique. Once you're given the subset to restrict, the restriction is a unique thing. But extension's harder, right? So, an extension of a given function, what you do is you're enlarging the domain, all right, such that the extension, if you restrict it to the given domain, well, you get back function again. So that's an extension. This theorem is very precious and useful. We should try to understand it, and we should try to use it whenever we can, because it saves us so much work. Here's the theorem. Actually, it's a proposition. Definitely mislabeled. This should be a theorem. But it's not that hard to prove, I guess. It's a proposition. I don't know. 4.33. Suppose, suppose beta is a basis for vector space V over field F, all right? And suppose W is also a vector space over the field F, all right? All right. Furthermore, pay attention to this. Suppose you have L, all right, as a function from not the whole vector space, but from the basis beta to W is a function. So what that means, right, that's just a sneaky way of writing that I'm telling you what the value of L is on this finite set of things on the basis, all right? I think I am assuming that the dimension of V, let me just say this. This might be, you might be able to extend this to infinite dimensions. I don't really know. I haven't really thought about it. So let me just say, let's assume finite dimensions since I haven't thought about it, all right? That's generally the case in this course. I'm not thinking very much about infinite dimensions, so you probably shouldn't assume that what I'm saying works for infinite dimensions. All right, so beta, a function. Here's the punchline. There exists a unique, and there exists with an exclamation point means there exists a unique linear extension. All right, extension of L to V. In other words, what I'm saying, to be more precise, what do I mean by that? I mean that you can find another linear transformation, let's say t, all right, from V to W, all right, such that what? Such that if you take t and you restrict it to the basis, you get back the given thing L, all right? That makes t an extension of L off the basis. If you make a linear transformation in this way, it's said to be, people do this all the time. They'll be like, I'm going to give you the values of the function on the basis, and then you just extend linearly. That's a very common way to construct a linear transformation as you go on in mathematics. Now, all right, what are we doing? So how do we prove this? Well, I want to prove there exists a unique linear extension from L to V. So here's what I do. Good proof. Proof actually mostly a calculation, so here goes. Let's see, we need to say V equals to what? Sum over I equals 1. Oh, I need to give some details here. The basis beta is, let's say, little v1, v2. I guess I'll let it be something else. How about f? f1, f2, fn. There's the basis for v. So suppose sum I equals 1 to n of, let's say, I don't know, use whatever letters you want. I'll use v for the moment. V sub I, all right, fi. That's a basis expansion for v in v. Okay. So this is the little v. This is the big V, the vector space. All right. So then I propose let t, all right, let t of v. Here's what I'm going to do. I'm just going to say it's going to be the sum I equals 1 to n and vi. And then what I'll do is I'll just use that on given, which is that L of fi makes sense. All right. So I already know that L of something in the basis is defined and an element of W. So like this formula makes sense at least. In other words, this L of fi is an element of W for each thing in the basis. And so there you go. That's my proposed definition. So you can observe L is linear. So if you let well, not L, observe T is an element of the linear transformations from V to W. I'm going to leave that to you guys, actually. That's a simple little exercise. You can prove that if you replaced V with V plus W, or CV plus W, what would happen is you would then write that in terms of the basis expansion. The coordinates of the CV plus CW would come out here, and then you'd be able to show linearity. It's just a short calculation. Is this a linear transformation? Yes. And is it unique? Well, yeah, I mean, it's unique because there's a formula for it. I mean, I'm telling you precisely how to write the formula for it. That's a unique, I mean, this is kind of a, we do these other arguments by uniqueness where we suppose you have two and such and so forth. But, if you have a formula for it, that does prove uniqueness. In this case, it does. And then, let's see here. Be careful with that idea, but this does suffice to prove uniqueness. All I'm missing is I need to show that T restricted to, and this is the easy part actually, T restricted to beta is in fact equal to L. So T restricted to beta, if we let that act on a typical thing in beta, which is what? F sub j, right? Well, that's equal to what? That's equal to that as well. Sorry. Yes, T restricted to beta of fj. So what is the? I need to figure out what is the. In my current definition, I have to figure out how to write this in this way, right? So like, let's see here. And I don't really need to have this restriction here. I mean, if I look at t of fj, that's going to... Let me just leave it. Okay, so this is t, by definition, t of fj, right? Fine, let me just get that out of the way. That's because fj is in beta, so this is the definition of restriction. Okay, nothing terribly profound there. And then the question is, what's the component? Well, this takes a little imagination. This is the sum, I equals 1 to n, of Kronecker delta, ij, fi. So that's a little sneaky trick for you. The coordinate vector of this has components delta ij like that. And so this delta ij plays the role that vi does in the definition, right? So this is equal to, by the definition of t, the sum, I equals 1 to n, of Kronecker delta ij, all right? Well, L of fi. Okay, well this Kronecker delta is the natural enemy of the finite sum. It takes everything and puts it to 0 except for one thing, which is where I is equal to j. So what do you have? You've got just plain old L of fj. Okay, well there you have it. We just showed that t restricted to beta acting on the jth element, the jth basis element in beta, is equal to L acting on the jth coordinate vector and basis vector in beta. So therefore, t restricted to beta is in fact just equal to L, which is to say that t is an extension. It's an extension off the basis. It gives us a linear transformation, in fact, from V to W. So what this means is for linear transformations, man, for linear transformations, this kind of thing doesn't happen. In fact, what this says is even though vector spaces are infinite dimensional in the infinite in terms of their cardinality, they're infinite. The plane is two-dimensional, right? But it has infinitely many points. The real line is one-dimensional as a real vector space, but it has infinitely many points, right? You shouldn't confuse cardinality, the number of things, right, with the dimension. Dimension is it's measuring something different than cardinality. Cardinality has to do with counting, whereas dimension has to do with our ability to build things from linear combinations with respect to a specific choice of field. They're rather different things. But there's a natural inclination people have to confuse cardinality with dimension. It's unfortunate, but true. And anyway, all this theorem is really telling you is that even though the vector space, if you think about it, at least for the choice of like a real number field or complex number field, even though there's infinitely many points in vector spaces of that type, knowledge about the value of a function on this finite set of points, this thing we call the basis, if you know the value of a function on the basis, you're stuck with the value of the linear transformation everywhere else. So linear transformations are really, really easy to pin down. And that is a great contrast to, say, these kinds of functions over here, where the possibility of extensions are limitless. So linear transformations are very, very structured. The problem of extending a given function in a mathematical theory is always an interesting question. We come to an interesting, like if you study the similar question in complex analysis, we learn there that if you have a function which is analytic, on like a little, I forget exactly the usuals, what a line segment will do, or a little open disk, or I think anything that has a, accumulation point? I can't remember the specifics. It's very, very flexible. If you have something that, if you have something that's defined on a little set like that, and if it matches with an entire function on some larger domain, then they have to be, the entire function has to be the unique extension, analytic extension of that. So there are kind of some similar theorems in complex analysis, but they're really a lot more complicated than this. This is the nicest extension theorem I know of. So, and I know you guys don't really believe me yet, but trust me when I tell you linear algebra is really some of the simplest math out there. Okay. Oh, so here's a typical example based on that theorem. If I tell you something like t of 1, 2 is equal to 3, 4. And if I tell you something like t of, oh, I don't know, 0, 7 is equal to 1, 1, that's enough data. All right, that's enough data to fix. This fixes a unique linear transformation t from R2 to R2. You see, that's enough. This is how that theorem I just proved plays out in action. See, because you can easily see that 1, 2 is not equal to k times 0, 7, right? So therefore, the set containing 1, 2, 0, 7 is linearly independent, and therefore a basis for R2, right? Which is two-dimensional. So if I have two things, I've got a basis. And so, knowing what 1, 2 maps to, and what 0, 7 maps to, that tells me uniquely what t is. Now, you're like, okay, so what is t? Well, then I'm actually going to have to do some calculation. Fine, you got me. I'm going to start with this one. That's the easiest thing. See, because what this is really t times what? Times what? 7 e2 is equal to 1, 1. See, that's really cool, because what that tells me, just translating, is that 7 times t of e2 is equal to 1, 1. Or in other words, t of e2 is 1/7, 1/7. But that's column 2 in the standard matrix for t, okay? So there you go. That's half of the battle is done. All right, so then, let's see, the standard matrix looks something like this. I'm just going to use some letters. So A, B, I don't know what those are yet. 1/7, 1/7, right? So I'm trying to find what A and B are. I know that this matrix times 1, 2 is equal to 3, 4. So can I figure out what the A and B are now? Probably. This is A plus 2/7 is equal to 3. And if you multiply this out, the second component gives me B plus, did I say 2/7? Yeah, I did. Oh, 2/7 again, isn't it? Duh, I can't. Eventually I'll learn how to multiply. 2/7, B plus 2/7, and this is equal to 4. 3 is otherwise known as 21/7. 4 is otherwise known as 28/7. So therefore A is equal to 19/7. Therefore B is equal to 24/7. And so there you have it. The standard matrix of T is equal to 19/7. Well, I'm going to factor out the 7. There's a 7 everywhere. So standard matrix of T is 1/7 times 19 and 24 for the first column. And then the second column was 1, 1. 1/7, 1/7. I factored out the 7. So if you want the formula, fine, I know some of you guys want the formula. T of xy is actually equal to 1/7. All right, 19x plus y, comma, 24x plus y. And then if I'm so crazy as to check my, oh, my shoulder hurts. If I can check my work, let's try it out. Plug in 0, 7, does it work? 0, 7, I get 7, I get 7, I get 1, 1. Woohoo! If I plug in 1, 2, x equals to 1, y equals to 2, 20, oh, 19 plus 2 is 21. 21 over 7, 3. And then 28 over 7, 4. Yeah, okay, good. So there you go, there's the linear transformation. It was enough for me to tell you the value of this linear transformation on those 2 points. Now, if I just told you I had a function from R2 to R2, it would certainly not be enough information to define the function. But because I told you this is a linear transformation, it's uniquely prescribed. All right, there's how the theorem works out in action. So beware of that idea. I use it a fair amount. It saves me writing. It saves us thinking. That brings us to probably one of the more important ideas that I'll share with you the entire semester. And this is the concept of isomorphism. What is an isomorphism? All right. By the way, the reason I was able to use standard matrix for that example I just did is because that was a problem about column vectors. I would caution you that you shouldn't probably be using the standard matrix unless it's that kind of context. If you've got an abstract problem, then you'll have to attack it a different way. And I'll hopefully show you some of that as we go on here. All right, so isomorphic. What is isomorphic? What's an isomorphism? Isomorphism is meaning same shape. All right. So here's the definition. We say a vector space V over the field and W over the same field, all right, are isomorphic. What's that mean? Isomorphic. If there exists an invertible linear transformation let's say psi, pitchfork if you like, from V to W, right? And I used L in the notes, whatever, you could put whatever, you could Pac-Man there for all I care, I don't know, whatever, just some letter for the mapping, okay? And in this case, we say psi is an isomorphism. An isomorphism, what is an isomorphism? I mean, more categorically speaking, an isomorphism is a bijection which preserves structure. And so it's a one-to-one and onto map, which is linear in this direction, but also the inverse should be linear. Now, fortunately, we already get that for free, so we don't need to, we can just be lazier and just to say, it's a linear transformation that's invertible, and as we talked about before, if we have linearity of the mapping, we automatically get linearity of the inverse mapping, which is super nice. Okay. More than this, we write V isomorphic to W in this case. All right. So let me just, what is this idea? Well, let me give you some examples actually to start with. I could give you the theorems, but let me just give you a bunch of examples and then we'll talk about the theorems. I'll change things up a little bit here. So I mean the first and probably most important example is that if you have a vector space V over the field F, right, with basis beta equals to, let's say, V1, V2, Vn, then we can define, okay, you can define phi beta, all right, phi beta is defined to be the following, so like the sum over, say, I equals 1 to n of x sub I, v sub I, all right, is equal to the sum, oh man, I missed my chance. Phooey. Oh well, it's too late. I've already written this much. And that changes to EI. Of course, this is an element of Fn. You might recognize this. In simpler notation, what I'm saying is phi beta, right, of V is equal to the coordinate vector of V beta. So this is the so-called coordinate chart, right? It's linear. Hey, you proved that in the homework. Isn't that convenient for me now? So you know that phi beta, right, phi sub beta, is a mapping, in particular from V to Fn. I would point out to you that this mapping is linear, and it is invertible. For shame, I could have, here, I missed my chance. I just proved this extension theorem and I failed to use it. Like we could define phi beta like this, right? I could just say, well, phi beta of Vi is equal to EI. So like the coordinate map, what it is a machine to convert the basis for the vector space to the standard basis. And that that defines the values of a function on the basis, and then you extend linearly, that's the coordinate map. And of course you can go the other way around too. The inverse, v beta inverse, well that acts on EI to give you back VI. So the inverse to the coordinate maps just changes the standard basis back to the abstract basis of the vector space. As simple as that. These are very useful. Yeah.
Sorry.
What do you need?
Oh,
Okay. Go ahead. Thanks. So those are of course useful relations. Now, where was I? So what I was getting to is this is an invertible linear transformation from the vector space V, which I'm assuming is over the field F, right, to Fn. And what this shows you is, of course, therefore, V with the dimension of V over F equal to N, right? Then V is isomorphic to Fn. An intuition for this is that if your abstract vector space is n-dimensional, in some sense it's really just n vectors over the field in disguise. That's a useful heuristic, but don't get too carried away with it. But it is a useful heuristic. Let's see here. So let me just kind of put this example into practice here. I could look at, say, P2, right, over the reals. So that would be the mapping. That would be the set AX squared plus BX plus C, such that A, B, C are real numbers. This is a set of real polynomials, and I could easily define the isomorphism psi of AX squared plus BX plus C to be A, B, C. Of course, you might recognize that that's nothing more than the coordinate map, right? This is phi beta is equal to psi if I let the basis be what, x squared, x and 1 for P2. So, but this is in fact an isomorphism of P2 to R3. In other words, quadratic polynomials are really just R3 in disguise. Another example, you could look at, let's say, something a little bit harder. I could contrast, say, m by n matrices, all right, over a field, and versus linear transformations from a vector space V to a vector space W, where V and W are over the field F. They're finite dimensional with the dimension of V equal to n, dimension W equals to m. I can prove, in fact, that these two vector spaces, we proved that was a vector space earlier today, didn't we? Yes, we did. We can prove that these two vector spaces are in fact isomorphic. In other words, they're really just kind of different notations for the same animal from the viewpoint of linear algebra. What's the isomorphism? Well, let's see here. Oh man, maybe I don't have enough technology to do this just yet. What's the isomorphism? I think I'm going to have to let that be. We're going to have to let that example hang there until we develop a little bit more terminology. Otherwise, I'm going to have to build a bunch of stuff from scratch for that example, which would be kind of out of order. All right, so I think we have enough. At least I have shown you a few things. So maybe you've started to see how we're going to find an isomorphism. Actually, what we can do, basically, is if we can send the basis of V to the basis of W, then, well, that's going to be an invertible transformation if you think about it a little bit. And it's going to be a surjection because if it maps to the basis, it maps to everything, given the linearity. So But how can that happen? Like how, you can only map a basis to a basis with a function if you got the same number, right, in both bases. So that's only going to work if we have the following theorem, and thankfully we do. If V is isomorphic to W, theorem. If V is isomorphic to W, then the dimension of V equals to the dimension of W. All right? So, how to prove this theorem? So, well, V isomorphic to W implies that there exists an invertible linear transformation, let's say psi, from V to W. But if V is equal to the span of beta sub V, all right, and the number of things in beta V is equal to, the dimension of V, of course, assuming that beta sub V is a basis, right? So suppose that's a basis, all right? Note that psi of beta V is a linearly independent set. It's a linearly independent set of vectors because we know that psi is an invertible map, right? We proved today that an invertible map maps a linearly independent set to a linearly independent set. And if you think about it, it must have the same number of things, right? Because if it didn't, that means it doubled up, which means there's a linear dependence. That's impossible because it's a linearly independent set, the images, which must have what? The dimension of V, vectors in it by counting. And, right? Now, how can I argue that the dimension of V has to be equal to the dimension of W? Now, of course, this implies what? This implies that the dimension of V, right, is less than or equal to the dimension of W. By that theorem, we worked pretty hard to prove that if you have a, how to say this? If you look at the span of these things, they have to fit inside W, right? So that means that you have at least this many linearly independent vectors in W. So that means that the dimension of V must be less than the dimension of W from this calculation. But on the other hand, we can also look at if beta sub W is a basis for W, right, then we can use the inverse mapping, which is also a linear transformation, right? Is linearly independent subset in V with dimension of W vectors, right? So that means that the dimension of W must be less than or equal to the dimension of V. I feel like we may have a theorem that shortcuts some of this work. I'm not looking at my notes, I'm just thinking there may be a way of shortcutting some of this, but anyway, here's an argument. But if you have the dimension of V is less than the dimension of W, and the dimension of W is less than the dimension of V, therefore dimension of V equals to dimension of W. This is one proof I give for this. There's another proof which usually appears in my mind when I think about this, and it's more based on the notion of coordinates. All right. But that was theorem 4.3.5. Let's see here, let me go on. Let me show you the other theorem, the other way to prove this, which I think is rather beautiful, and actually gets me closer to explaining to you how to do some of your homework. I know. Guess I need to erase. Yeah, we can. All right. So. All right, so, and actually we'll get back to that example over there too before we stop here, hopefully. All right, so the theorem again was that if V is isomorphic to W, then the dimension of V must equal to the dimension of W. And we are assuming that V and W are finite dimensional vector spaces, otherwise, all right, I have to think harder. We don't want that. So, consider this. There exists beta sub V and beta sub W, right? Bases for V and W with the number of vectors in beta sub V equal to the dimension of V, right? And the number of vectors in beta sub W equal to the dimension of W by definition of dimension. Number of vectors in the basis is the dimension. And then you can construct, well, we can construct the, fine, I'm stuck with it. The coordinate vector, phi sub beta, I've got subscripts with subscripts, it's annoying. So this gives me a one-to-one mapping, which is surjection, an isomorphism, right? I have the isomorphism of the coordinate map that goes from V to F. And I need to give this a stupid name. Let's call the Vn, let's call the Wm, so Fn. And likewise, the coordinate map for the W basis gives me a mapping from W to Fm. And we can do this by, say, phi beta sub V. Well, I already showed you how to define the coordinate maps. So you define them in the same way. Let me not write all that out again. These are the coordinate maps, all right? So here's a picture of what's going on. Here's V. Here's W, right? I've got this map, phi beta V, down here to a copy of F N, and I've got this one over here to a copy of F M, all right? And we also have a mapping that's given to us. There exists an isomorphism between V and W, right? So there's this invertible linear transformation right here, psi. Okay? And so if I can get a mapping that goes from here to here, then I can just argue that n equals to m if I think about it, right? So how do you get a mapping that goes like that? Well, use your imagination, right? I can either go from here to here directly, right? Or I can take a longer path. I can go like this. Like that, you see? And so this first part of the journey is the inverse mapping of phi sub beta V, right? The inverse coordinate map there. This, of course, is psi. And then over here you have the phi beta W map, right? So now this is the partly tricky part. You have to think about function composition. And so what we have here, this mapping, which I'm going to write over here so I can see it better, is we've got, all right, so the one that comes last comes first. So phi beta W composed with psi composed with phi beta V inverse. All right. Now the wonderful thing about this blue arrow I just defined as this mapping here is it's the composition of linear transformations. That's a linear transformation, that's a linear transformation, that's a linear transformation. But guess what? The composition of linear transformations is a linear transformation. Okay, I proved it for 2 earlier today, but you can easily extend it to n by induction. Certainly 3. And, better yet, because each one of these is invertible, this is also an invertible linear transformation. In fact, I can write the inverse for you if you like. The inverse of it would be equal to phi beta V composed with psi inverse composed with phi beta W inverse, basically by a sock shoes identity which exists for functional inverses. And of course you could also follow the red arrow the other direction, like like that. So the point is, hey, this blue arrow is an invertible linear transformation, which means it does what? It maps basis to basis. So the only way that could happen is if n is equal to m. Otherwise, you could take the basis here and transfer it to another basis over here, which had a different number. That violates our dimension theorem, which is impossible. And there you have it, a different proof, which I like actually, by the way. All right, so finite dimensional vector spaces, if they're isomorphic, have the same dimension. I will spare you, but proposition 4.3.6, I proved that isomorphism is an equivalence relation. In other words, if we have that V, V is isomorphic to itself. If V is isomorphic to W, that implies that W is isomorphic to V. And finally, if V is isomorphic to W, and W is isomorphic to U, that implies that V is isomorphic to U. So it's reflexive, symmetric, and transitive. This, of course, is wonderful because that means that isomorphism is an equivalence relation on the space of all vector spaces. So what that means is it partitions the space of all vector spaces into equivalence classes, as hopefully you learned about in Math 200. I hope you did. Anyway, if you have an equivalence relation that partitions the set into disjoint classes, and it turns out these disjoint classes are all the vector spaces in a given equivalence class, how are they labeled? Well, it's kind of not that exciting. They all have the same dimension, so the dimension labels the equivalence classes for a given field, of course. You can divide, you've got one-dimensional vector spaces, two-dimensional vector spaces, three-dimensional vector spaces, and up the chain. All right. So it's, and I have, as is my custom, a stupid number of examples in my notes for you to look at. Oh, one of the ones I'm very fond of is the proof that m by n matrices is isomorphic to n by m matrices. You get that one, the isomorphism is just transposition. That's kind of cool. All right, I like that one a lot. Anyway, I've got a bunch of examples of isomorphism in the notes I'll let you look at. Okay. All right, finally we have come then to the topic that will be occupying our next lecture. And I'll try to show you a good example to get us started on this. And it's almost in the water here with this proof, is the notion that we can write, what's missing for abstract linear transformations, right? What's missing for abstract linear transformations is the idea of the standard basis, all right? Or the standard matrix, right? For a linear transformation, of column vectors, we have a standard matrix, right? But if you have a linear transformation, say T, all right, and suppose it goes from, say, P2 over the reals, all right, and suppose it maps over here to, I don't know, maybe it maps to like R2 by 2, okay? And the formula for the linear transformation could be something like this. T, f of x, all right. Let's see, let's suppose it goes to f of 0, f prime of 0, f prime prime of 0, and then 0. I don't know, whatever. There's a silly mapping. You can prove this is a linear transformation, right? But how could you write it as a matrix multiplication, right? That's the thing. There's a standard technique for doing this. Let me show you. So what you got to do, all right, is you got to pick a basis for the domain and a basis for the range. So here I'm gonna make a choice. So P2R, I'm gonna say is the span of, let's say, 1x and x squared. Okay, I'm gonna use this as the basis, so-called beta. And R2 by 2, my default for R2 by 2 is just to use the matrix units in lexicographic ordering. So this is, I'm going to say that's the span of like E11. Just read it off the rows. First row, then like the second, right? Like this. That's the order I usually put them in. That's my I mean, it's not a standard basis, but it's my standard choice for the basis there. Let's call this set gamma. Okay, so beta and gamma are bases